Thank you. The next presentation is going to be presented by Tyler McGrew. Tyler McGrew received a bachelor degree in electrical engineering from Miami University in 2021 and a master's degree with the Center for Power Electronics System, Virginia Tech in 2023. He's currently working towards the PhD degree in electrical engineering with CPES. His research interests includes modeling and the reduction of electromagnetic interference and high-frequency power conversion and magnetics. His presentation title is Effect of Parasitic Magnetic Couplings on EMI of GaN-Based PFC Converter. Tyler, welcome.
Thank you, Dr. Dong. And thank you, everyone, for attending our EMI session this afternoon. So I'll begin our presentation titled Effect of Parasitic Magnetic Couplings on EMI of GaN-Based PFC Converter. So as we know, EMI can be one of the most difficult aspects of power supply design. And in particular, for front-end power supplies, we have to meet some regulatory conducted EMI limit, as well as radiated limit. Of course, we can add some EMI filter. In theory, this is not a very complicated process. We put a low-pass filter, which will attenuate our conducted switching noise, and then we can meet the standard. The problem is, we can add the filter, and sometimes our EMI is still too strong, or the filter is not effective. And typically, this is because of parasitic elements, as well as parasitic couplings, both within the EMI filter and also between the EMI filter and the power stage. For example, here is a PFC converter with EMI filter. And if we measure the magnetic field above this power supply, we find a very noisy switching magnetic field, which is kind of radiating from our PFC power stage. So in other words, there's some stray magnetic flux, and this can spread not only around our PFC power stage, but it can spread to the EMI filter or even other sensitive circuit components. But in particular, this can actually induce switching noise within the filter components and thereby increase our conducted noise. So my goal today is two things. Firstly, we'd like to be able to predict the EMI while accounting for these parasitic magnetic coupling effects within the power supply. And we'd like to be able to predict this before we build the hardware, ideally. So we can actually use the FEA simulation model as well as the circuit model in order to predict this EMI. And the second thing is, once we understand the EMI behavior, of course, we want to mitigate it and reduce these couplings to reduce our EMI noise. So for this hardware, we have a kind of an EMI evaluation board. So we have a single channel totem pole PFC, which means we have one high frequency half bridge. Here we're using these topside cooled gallium nitride switches. And we're operating at a critical mode high frequency, which allows us to use this PCB-winding integrated inductor in our power supply. And finally, to attenuate our noise, we have this EMI filter for our AC power lines. Now we're going to develop a DM noise model, which has been done before many times. So we can assume that our LISNs are a perfect 50 ohm impedance to measure our EMI from each power line to the earth ground. And in order to model the switching action of our PFC power stage, we can replace the full bridge here with an equivalent EMI noise source. So that's going to be called VS, which is our switching voltage, and that's defined here between the two switching nodes, the high frequency and line frequency switching points. So here I've replaced these switches with the VS EMI noise source. And finally, we're just going to include the parasitic elements of the EMI filter. So for example, the series inductance, series resistance, or the parallel capacitance and parallel resistance. Now that we have this model, let's analyze this EMI noise source VS. So as I said, this is between the two switching points. And for this converter, that voltage is basically applied to our AC power lines. So here I've measured the actual switching voltage based on our hardware prototype. And because this is a PFC, we have the positive and negative half-line cycles. And in this case, we're doing a critical mode PFC modulation, which means we're also doing a varying switching frequency and varying duty cycle throughout each half-line cycle. So for example, if we look at one point in the line cycle, we can see a relatively larger or higher switching frequency. And at another point in the line cycle, we see a lower switching frequency with a different duty cycle. Then we can look at the frequency content, which is really what we're interested in for EMI analysis. And we can see our variable switching frequency. In this case, it's between 300 and 800 kilohertz, and then all these subsequent harmonics. Now, a nice thing is we don't have to actually measure this EMI noise source. Based on the blanking time and the switching frequency, which are things we usually know ahead of time based on our PFC operation, we can actually just crudely approximate this waveform with some type of square wave. So for example, here I've approximated our real measurement just based on the blanking time and the switching frequency throughout the line cycle. And here's the 2 points, which I showed before. And we can see our approximation is very similar as the measurement, only we're neglecting some details such as the rise time and fall time of the waves. And if we overlay this frequency content with that of our measured VS, we see that we can approximate this EMI noise source very closely just with such a simple approximation. Now we have our switching noise source, EMI noise source, and we have our DM noise model. We should be able to predict our conducted EMI, DM noise. So what we're going to do is multiply our switching voltage by this DM noise gain. So this is just a transfer function defined by our EMI model. So in this case, we have this EMI filter, which attenuates our noise versus frequency. And as a result, when we predict our noise, the prediction is very low in magnitude. But then when we do the measurement, we see our prediction is way off. So the real EMI is much larger than we predict with this initial model. And this is because of parasitic couplings between the power stage and the EMI filter. There's a really easy way we can demonstrate this. We repeat the same EMI measurement, except we move the EMI filter just outside of the chassis. And in this way, we can mitigate any coupling between the PFC power stage and the EMI filter. And when we do this, we see the EMI is reduced by 40 dB, as much as 40 dB, and it also matches very closely to our DM noise model. So this is just a demonstration of this magnetic coupling effect. So our initial model is not accurate. We cannot really predict the behavior of the circuit. So we could include all of the magnetic couplings in the circuit, but this quickly becomes excessively complicated. And not only that, but many of these couplings are not actually important for the EMI noise behavior. So we don't need to include every possible interaction within our circuit. Instead, we're just going to focus on 3 key magnetic couplings, which we've identified that can allow us to predict our EMI very well without having such a complicated circuit model. And in order to predict the values of these couplings quantitatively, we can use a 3D FEA model and extract these couplings within our real converter layout. So we'll look at these one at a time. The first magnetic coupling is between our PFC inductor L1 and this parasitic LP. LP represents the parasitic loop inductance of our input power cables, but these power cables are outside the chassis. So we actually don't need to worry about this coupling, except there's a small termination of our power cables at the input of the EMI filter. So this is kind of the pass-through or termination inductance of our input power lines. And because there's some small loop inside the chassis, that means we're going to have some voltage induced in this loop by the stray magnetic field of the PFC. And based on our simulation model, we extract this, excuse me, we extract this coupling value as 0.48 nanohenry. And another important one is the coupling to our input capacitor, CX1. So this one also has a series inductance, which represents its equivalent current path through the capacitor. And therefore, we can also have magnetic coupling into this capacitor from our PFC. And this has a smaller value of about 0.1 nanohenry, and it has the opposite polarity. And finally, the magnetic coupling to our common mode choke is very important. So because the choke has 2 sets of windings, we can actually have a DM noise induced as well as a common mode noise induced. But right now, we're just going to focus on the DM induced voltage. So we'll define this as MLY DM. And because the common mode choke has a large number of turns, as well as a very high permeability core material, we find that this magnetic coupling is very strong, about 80 times as large as the next strongest coupling. So it's almost 40 nanohenry. Now we're going to analyze our noise model with these magnetic coupling effects to see their impact. So here's our original model with just the conducted noise, which flows through the EMI filter. And because this flows through the filter, it's effectively attenuated versus frequency. However, after we consider the effect of this coupling to our input loop, we see that this DM noise by this magnetic coupling has a much stronger magnitude through our whole conductive frequency range above about 200 kilohertz. This is because any current induced by this coupling MP is going to be directly applied to our listen. It's not attenuated by the filter. And that's why we see this flat magnitude response versus frequency. It's a similar story if we look at the DM noise induced in our capacitor. This one has a smaller magnitude, which is why we see it has a lower DM noise magnitude. However, it has a very similar noise path. It also has the opposite polarity, so we do see a 180 phase shift between these two orange and pink curves. And finally, if we look at the DM noise by our CM choke, this one has the largest magnetic coupling value. However, it's not necessarily the strongest DM noise effect. And this is because the current induced in our choke will be partially attenuated by our input capacitor, CX1. So this one has a more complicated frequency response. At low frequency, it has even stronger value, but then at high frequency, it's less significant. And then our total DM noise is now a function of all these magnetic couplings as well as our conducted noise path. So we're going to go back and predict our DM noise again in order to validate this model. So if you remember previously, it was way too small compared to the measurement. But now if we consider just these three coupling effects, we find that our DM noise that we predict matches very closely to our actual measurement. And this was all done just by approximating the voltage source waveform and then extracting these three coupling values in FEA simulation. So now I have some understanding of the EMI noise behavior. We want to be able to actually mitigate these problems in order to reduce our noise. So there's different approaches we could take in order to reduce our EMI. One approach would be to change the layout of our power supply. We'd like to move the filter further away from the PFC stage, and that could reduce this effect. However, this is not always ideal or feasible because we're probably going to have to increase the size of our layout. Another approach would be to add some shielding material. For example, we could put a copper or aluminum or a high permeability shield between our PFC and filter. And this can be very effective. However, this could add some cost or manufacturing complexity to our design. So that's also not optimal. So there's two approaches we're going to look at that have the least amount of downsides. The first is if we can improve the design of our power stage magnetics, for example, our PFC inductor, in order to contain the magnetic field so it's not leaking as much all around the power supply. And the second approach is if we could actually modify the layout of our EMI filter in order to reduce its susceptibility to external magnetic fields, for example, from our power stage. So we'll start with the PFC inductor design. So in our original design, we have an air gap on the outer leg and center post. And if we look at the simulated magnetic field intensity, we find a very strong magnetic field just next to the air gaps on these outer core legs. And as we move away from the inductor, this magnetic field then gradually becomes weaker. We can demonstrate this effect of the air gap by doing two more cases with different air gap. And all three of these have the same inductance value, which means we're storing the same amount of magnetic field energy. If we increase the air gap even further to 1 millimeter, our magnetic field outside the inductor is increased even more. And of course, if we eliminate the air gap on the outer leg, that's our best case scenario. And we find the smallest amount of leakage magnetic field or stray magnetic field outside the inductor. So ideally, we'd always like to have no air gap on our outer legs of our core. However, even if we have no air gap, we'll still see some stray magnetic field. So here's a simulation repeated with no air gap on the outer leg. And one reason for this is the reluctance of the core itself. So we know that the magnetic field is going to be about approximately proportional to the reluctance of this outer core leg, and that is inversely proportional to the permeability. So we can demonstrate this effect by using a higher permeability material in our simulation, and we find about a 3 times reduction in our leakage magnetic field. So not only ideally we'd have no air gap, we'd also have a very high permeability core. And to demonstrate this, we've made 3 prototypes. This inductor design A is our original inductor prototype. And if we measure the magnetic field at the EMI filter location, we see there's a very strong magnetic field from the PFC inductor. For our second design, we've just removed the air gap from the outer leg, but we keep the same inductance by adjusting our center post air gap. And by making this change, we find about a 20 dB reduction in our magnetic field at the location of the EMI filter. So we're containing this magnetic field much more effectively. And finally, we use a different core material with a very similar geometry. And this one has about 4 times larger relative permeability. And we find about a 7 dB additional reduction in our magnetic field. So we've seen this magnetic field is effectively contained by our inductor design. How does this affect our EMI? So in our original case, all 3 of these magnetic coupling values had a relatively strong effect on our DM noise. So as a result, our measured DM noise is very strong. After we switch to the improved inductor design, B, we remove the air gap and we repeat our FEA simulation with our 3D model. And we find that all 3 of these coupling values are significantly reduced. And based on these couplings being reduced, our DM noise is also reduced. And we see a close correlation here between our prediction as well as our measurement. And finally, if we just use the higher permeability material, we predict about an additional 2 times reduction in all of our couplings. And this corresponds to about 6 dB further reduction in the DM noise. So not only can we get a good reduction, but we can also predict this reduction based on our EMI model, as well as our FEA simulation. However, we're not always able to adjust the design of our power stage magnetics. So oftentimes, the EMI design can come at the end of the power supply, and we've already have an optimal magnetic core or magnetic design. So another approach is to improve the filter layout in order to reduce the susceptibility. So originally, we had this vertical CM choke, which had a very large coupling to our PFC inductor. We can just use a different package for our choke. So here I have a horizontally mounted CM choke. Actually, it's from the same vendor with the same inductance and impedance characteristic. But with this one, we have effectively minimized the coupling to the choke just by changing its orientation. So from about 40 nanohenry to less than 1 nanohenry. However, we find only a small reduction in the DM noise. And we can explain this by going back to our EMI model. So originally, all of our magnetic couplings are having some effect on our EMI. Although we've minimized the coupling to the CM choke, that only reduces one of these coupling paths, which is this blue curve here. So originally, this blue curve has a strong effect at low frequency. Now we've reduced its magnitude, but our EMI is still going to be determined by these other 2 couplings, in particular, MP coupling to our input power loop. So if we want to have a further reduction of our DM noise, we need to mitigate this coupling effect as well. So here's our original case. We have 0.48 nanohenry. As a result, we still have a strong DM noise profile. We can make a very simple change in order to minimize this coupling. So we need to reduce the size of this loop from our power cables to our filter. We've already tried to make this loop as small as we can by putting the filter up against the chassis wall. However, there's always going to be some loop here, just physically. We can instead just twist the leads one time, which is a very simple approach, but this can allow us to cancel the magnetic coupling to our input loop. And in this way, we can reduce this coupling from 0.48 to 0.15 nanohenry. And we see a very good reduction in the DM noise. Now we can even meet the Class B limit for our conducted EMI. So to summarize, we've seen that magnetic couplings between the PFC stage and the EMI filter can significantly increase our DM noise by more than 40 dB. And we've developed a EMI model which just includes 3 important couplings or critical couplings. And we can extract or predict these values using the 3D FEA model. And by combining this analytical circuit model with our predicted values from a 3D simulation, we can predict our DM noise spectrum. And then we have 2 solutions to mitigate this effect. One is we can modify the design of our power stage inductor, or we could improve the layout of our EMI filter. And using either of these approaches, we can meet even the Class B limit for our EMI. So thank you very much for your attention, and I'd be happy to answer any questions.
Thank you, Taylor. We have a few minutes for questions.
Tyler, is this on? Yeah. Nice paper. Eric Person from Infineon. How did you go about modeling the capacitor? Could you talk about that a little bit? Like from an, you're doing what, Maxwell or something, 3D FEM.
Right.
Did you just make it a simple loop, or do you actually model the inside of it, or how did you go about?
Oh.
I mean, because to me, it
Sure.
looked like you're going to have overlapping plates
Right.
that I would think would cancel, but how did you come up with that?
That's a very good question. So this is an important point of, one moment, let me pull up the image here. This is an important aspect of the 3D model, obviously. And let me just zoom in here. And there's a few papers that I found that talk about this that I kind of based my 3D model on. But the interesting thing is we know the inductive loop is formed by the leads on the outer edges, and then we have some capacitive body in the middle. And we can basically model this whole body, which is a series of plates and dielectrics. We can model this as a lumped conductor because by the equivalent current path, it can just flow through any of this with a very low impedance. So actually the main characteristic of the loop inductance is just the leads and the relative geometry of the winding itself. I mean, the capacitor winding itself. And another interesting thing is, although we have a conductive foil or conductive layers within our capacitor body, these are actually so thin that they don't have much eddy effect at all. So although we have some magnetic coupling to this capacitor, there's very little cancellation by eddy current within the capacitor because the spray is so thin.
Dr. Lotfi from Deep Science Ventures. Very nice talk. Thank you.
Thank you.
I'm wondering, based on your work, your experience, all the hours that you put into this, do you think it might be possible at some point to use the finite element simulation as a design tool to actually design the physical layout ahead of time to meet an EMI spec? I think if given a few years, it might be possible.
Thank you. That's a great question. And that's actually exactly what we're trying to work toward. So this is one demonstration, and we've used a relatively simple hardware. We only have single channel PFC with a filter. I mean, the real case, we're going to have, depending on the application, we'll probably have a second stage, probably have multiple channels or a 3-phase system. But I think that's definitely possible. I think we've demonstrated it here for DM noise for one converter, but it should apply generally. And if you look at CM noise, we can do a very similar approach, and we can predict the capacitive coupling with FEA. And then, of course, we could extend this to more complicated hardware. So I think the FEA simulation is powerful enough, and we have the, the tools. We can do that. Yes. Thank you.
Can I have one more question?
Definitely.
So this is a great work. I really like the idea that we can predict these things and how they work. Could you elaborate a little bit? How did you come up with which are the important coupling factors? Because if you will change the layout and the geometry, that might not be the one. So you always have to kind of look at the layout and take your judgment, which are the important factors. It's actually a very nice work because it really proves what we kind of figured out from practice, that you turn the choke and you shield it and of course no outside air gap, showing it that it actually supports these is great and perfectly matches our 30 years of experience. But which are the 3 couplings? Why it is 3? Why not 4? And how do you get there?
That's a very good question. So yeah, you're right. There is a lot of dependence based on your layout, which ones could have a stronger impact. But we do have one kind of rule of thumb, which is that even if you have a 2-stage EMI filter or a 3-stage EMI filter, whatever stage is most is closest to your listen or your measurement is going to have the strongest impact. So even if we had a stronger coupling to a different stage, it probably wouldn't have much impact because that coupling itself would be attenuated by the filter. There is one coupling that is also important. I didn't include it here to make things a little bit simpler. And that is actually between the choke and the capacitor. So the LC coupling, if you remember from previous CPES work, that actually affects the series inductance value. It changes the effective inductance of the capacitor. And so there are some other couplings that have a significant impact. It's kind of case to case, as you say. But I mean, theoretically, you could just put all these in your simulation. You don't have to just limit yourself to 3. Just a
Oh,
few.
I like the idea that I only have 3.
Okay, good.
Maybe one last question.
Sure.
All of your high frequency content was very well suppressed. That's suppressed. There was nothing. It was just a constant decaying thing. But we know around above 15 megahertz, you start to see an additional peak where magnetic and electric fields starts to convert
Oh, okay.
from one to the other.
Yes.
And I didn't see that in any of your results. How did
Um,
you eliminate that effect?
I believe I understand what you're talking about. And some of my previous measurements, I see a high frequency DM noise spike. And that was because of a capacitive coupling between the power stage and filter. So usually a capacitive effect doesn't have a very strong impact on the DM noise, but a high frequency it can. Actually, in this case, we've already shielded the capacitive couplings, and that's why we don't see this effect. So based on some of our previous work, we're able to have some electrostatic shield inside of the PCB windings. So we already minimize this capacitive coupling, but yeah, in real case, you would probably also need to include this effect as well.
Okay, thanks.
Thank you.
Thank you, Tyler, for your very nice presentation. Thank you. So the next one will be presented by Qiang. Qiang is currently a PhD student in CPES at Virginia Tech. He received bachelor's degree from Ho Hai University